Welcome, everyone. We're just waiting for further participants to join us, and then we will slowly start today's webinar. So we're just waiting a little bit. Welcome, everyone. Once again, we're still waiting a little bit for further participants to join us. Okay, so welcome once more, ladies and gentlemen. My name is Efi Apostolidi. I'm a postdoc research associate at the Institute of Structural Mechanics and Design at the Technical University of Darmstadt in Germany. And I'm very happy to assist in the moderation of today's webinar. Let me briefly share my screen with you. Okay, I guess that everyone who is here already knows that this webinar is organized by the International Association for Bridge and Structural Engineering, the so-called IABSE. And IABSE's mission is to exchange knowledge and advance the practice of structural engineering worldwide, considering all aspects in structural engineering, all types of structures and structural materials, all aspects of the construction process, counting over 2,500 members in 100 countries. IABSE is also very active in terms of publications. It has its own journal, Structural Engineering International, IABSE bulletins and conference proceedings. The voluntary work of IABSE mainly is divided in and coordinated through task groups and the national groups. The task groups are divided in 6 technical commissions on the topics of performance and requirements, conceptual design, structural analysis and evaluation, construction methods and processes, existing structures, and sustainability. Please feel free to look it up in the IABSE webpage and contact further experts if you would like to share your expertise on these topics. As mentioned, IABSE also has national groups that organize several events in the form of seminars, workshops, technical visits, and so on. And we have also the main IABSE events, and the upcoming ones in 2023 is the IABSE Symposium in Istanbul on long span bridges, and there is a new date of the conference of the symposium by the end of April 2023. And we also have the upcoming IABSE Congress in New Delhi by September 2023 on the topic of engineering for sustainable development. We might also say that the abstract submission deadline has been extended, so if you're interested in submitting a paper, please do so. IABSE also has a young engineers program and students membership. Also, please look it up on the website and see what the student membership has to offer. And a special offer for today, as it is Black Friday, we have a membership promo, like 30% off for all new applications for IABSE. So if you're interested, please hurry. So, as you already know, today's webinar is entitled The Structural Engineer and the Current Climate Emergency. This is a webinar in the framework of Task Group 6.1, Effects of Climate Change of Infrastructures, chaired by Andre Orchesi. You can find in the chat further information on this task group. And it is also organized by the IABSE British National Group. Together with us is Ian Firth, the chair of the British National Group. He's a structural engineer and a bridge designer with a portfolio that stretches from the longest to the shortest bridges. He's the only structural engineer to give a TED talk on the main stage, and he has spent almost his entire career at Flint & Neil, now part of COVI, and he now operates as an independent consultant. And before I give over to Ian to introduce today's speaker, I would like to ask you to place all your questions in the Q&A section of Zoom. And after the presentation, we will try to address as many as we can, given the time frame. And finally, I would like to inform you that today's webinar will be broadcasted live on the Facebook page of IABSE, and it will be recorded and uploaded to the e-learning page of IABSE. I think this is all the general information from my side, so I give over to Ian.
Thank you so much, Effie, and hello, everybody. It's a pleasure to be with you, particularly on this extraordinarily important topic. You will all have, I'm sure, in your own way, have been grappling with the implications of the climate change and climate crisis, climate emergency, indeed. And so good to see you all here. There's, a plethora of stuff being written and talked about. And I think it's really important to get really focused on how we as structural engineers can make a difference. So I was delighted when Lee suggested that she should lead us in this webinar today. Lee Frank, somebody I've known for many years. She was originally with Arup, and then after some years with Arup moved to New York, where she worked with Guy Nordenson Associates, now works as an independent consultant. Lee was part of the international of IABSE, part of the British group of IABSE all those years ago when she was with Arup, and in fact it was Lee largely who was responsible for getting the Future of Design event off the ground. You may know of that. Certainly those of you in the UK will know about it, but it's something which has been very impactful, actually, particularly among young members. But Lee is an engineer, and I'm not going to say any more about her or me. We'll talk more later on. But thank you so much, Lee, for leading us in what I hope is going to be the first of a series of webinars, seminars, workshops, whatever, where the British group is going to lead on. The British group has been doing quite a lot already in this arena, and I'm delighted that Lee is going to lead us off on this new wave. So, Lee, over to you.
Thank you, Ian. Thank you for the introduction. Okay, so let me share my screen with you. I hope you can all see it. So yes, I'm really excited to give this talk today. I think the motivation for this was really that, there's so much information coming up about this topic now. So maybe say 3-4 years ago, it would have been difficult to really get all this information together and start working on it. But now it's out there. But what I see is it's not really evenly distributed amongst all of us. So the idea to give this talk with IABSE is really because it's this global organization and we have the chance to really spread this knowledge. So I'm excited to see there were people from 30 countries who signed up for today. So thank you for being here, and also in time zones where it might not be so convenient for all of you. So thank you. Okay, a little bit background, Ian already mentioned it. So I've been working for 10 years as a structural engineer. I got involved in different projects. You can see some here on the screen, from buildings, high-rise, a lot of museums, a lot of sculptural projects, bridges. But the point I really want to make here is that, my background is I'm a designer, probably as much as a lot of other people here on this webinar. And it's really been the last years that I've started to build up my knowledge on this topic of sustainability and embodied carbon. And so it's now that I specialize in this, I'm independent in Luxembourg, and I'm trying to help the rest of the industry, be it other architects, engineers, the industry, to really get up to speed with this, because it's so important and it's time critical. So based on my background, I will focus the talk mostly on buildings today. And you'll also see that it's a little bit heavy on the European context. I'd be really interested to have this discussion also with other people from IABSE, from the US and Asia and Africa and different places, so that we can really compare notes. And I think the other point I just want to make, the information I'm sharing with you is really information that I've gathered from many, many sources. So a lot of this has been produced by other engineers out there who should really get the credit for it. But I'm going to frame it and kind of tell the story maybe in the way that I understood it through the past years. So to get started, a little bit of context. This is probably nothing new to most of you, but I think it's just important that we make it clear where we are at. So it's a graph which is showing the carbon emissions over the last 30 years. They keep on rising. We can see that punctual events, financial crisis, COVID make a little bit of impact on this, but we just continue going on the same trajectory again. And this is also, just to make clear, these are annual values, not cumulative. So it's really every year we are getting a little bit worse. And also, unfortunately, a lot of these conferences that we had not really made an impact on this. As a consequence, we all know temperatures are going up. This is a graph which is showing temperatures from like mid-1950 as compared to pre-industrial level, which we call a reference period between 1850 and 1900. So now we are at about, we're a little bit over 1 degree global warming. That was in 2017. And we are on track for 1.5 degree warming within the next 10-20 years. And the 1.5 degrees warming is important because at this point we talk about something which is called runaway climate. So we will have consequences that will be very difficult to deal with. And if we don't do anything, we're actually on a track to end up at 3 degrees by the end of the century. And of course, it's not just about the temperatures in itself, but it's about all the consequences of this. So what we see is, with these temperatures, the risk of extreme events is going up. We talk about floods, droughts, heat waves, Arctic melting, sea level rises, loss of biodiversity, reduction of crop yield, risk of starving, and the migration that is going with this. We all know this. We can start feeling it. But I think the point to make here is that there is actually a significant difference if we talk about 1.5 degrees or 2 degrees. Risks are going up, and the people who will be feeling this will also, of course, increase. So what do we have to do? We've been told that we have to limit global warming to 1.5 degrees. This is something that was produced by the IPCC. And we know that to get there, we will need to have far-reaching and rapid and unprecedented changes to all aspects of our society. So just to show, this is again the same graph, just in a different version. Carbon has been going up, but to get us on track, we have to get to net zero carbon emissions by 2050. So it's really showing, we have to change how things have happened in the past quite drastically. So one way that I feel is a little bit easier for me to get my head around is not just thinking about net zero by 2050 and to limit global warming to 1.5 degrees, but I like to use this notion of this carbon budget that we have left. So for the moment, we are emitting about 1,300 tons of CO2 every second. So if you then look, in order to limit the warming to 1.5 degrees warming, we have about a budget of 280 gigatons of CO2 left. And if we continue at the current speed, this will give us about 6 to 7 years to get there. And it's really, for me, to think about this carbon budget helps, because every time we take a decision, be it in our lifestyle or be it through our work, we're really starting to pull on this budget and making it reduce quite quickly. The graph on the right shows it's not just about getting to net zero by 2050, but how we're going to get there is also quite important. The green line is showing what is in line with the 1.5 degrees warming. But so it basically shows that we have to do something drastically quite quickly, and then we know towards the end, when it's getting more difficult to curb carbon, maybe that will be a bit slower. But the orange line is a little bit more what we might be doing, or what we're currently on track to be doing. So we might be a little bit slow to start. And what this means that basically the area under the graph is the total carbon emitted. So if you think of the carbon budget, the difference of how we're going to get there is quite important, because if we are on the orange curve, we'll have emitted about twice the budget that we have left, which will of course lead to more than 1.5 degrees warming. I think just quickly, of course, we will talk about carbon today, but I think it's important to keep in mind that it's not just about carbon. There are many topics that come into play when we talk about sustainability. This is also reflected in the Sustainable Development Goals and also in a lot of the assessment methods about sustainability on projects. And, when you start to influence one, it really has also an impact on the other. So it's difficult to pull out carbon, and we have to really keep the big picture in mind. To me personally, the way I go about it is that I feel that if I focus on carbon, I can also have a significant positive impact on all the other topics. So as long as I don't lose the big picture out of mind, I think for us at Structural Engineer, it is important that we really, really focus on this topic of carbon, and that we work with other professionals within our design teams to also keep an eye on the others. Now, okay, we've set the scene for where we are at globally in terms of our kind of emissions. Let's see where the structural engineer fits into all of this. I think the first thing to look at is, how does our industry compare to other industries? So the building industry compared to maybe transport or other industries, the wider construction industries. And what we see here is that when we talk about buildings, the building industry is responsible for about 40% of CO2 emissions globally. So that's all you can see in green. And that's, of course, some of it is energy, some of it is the materials, but this is really, really kind of the big picture, all of this. And this is also why today in this talk, I will be focusing on buildings, knowing that, of course, there's also infrastructure that also merits talking more about. Now, when we talk about carbon in buildings, there's really one differentiation to make. I'm sure most of you are aware of this. but there's on one side the embodied carbon and on the other side the operational carbon, and these together really is what we call the whole life carbon of a building. Embodied carbon is when we talk about the carbon that goes into taking the materials out of the ground, transporting them, manufacturing them, bringing them then to site, and the actual construction of the building, together again with the carbon linked to the maintenance of the building, and then in the end, how to get rid of it. The operational carbon is more about what is the CO2 that goes into operation. So heating, cooling, ventilating, lighting, power, and all of this. And to make it simple, embodied carbon, think about the stuff, think about everything you can touch. Operational carbon, think of everything that you can turn on and off. So of course, embodied and operational carbon, we want to know when we look at a building, how do these two compare? And it depends on many things. It depends on the type of building, on where you're located, and so on. But I think one important thing to understand is that the relationship between the two has changed over time. So operational carbon used to be the big chunk. So this is what's shown here in gray. And the embodied carbon may be the smaller part. But as we move through the years and where we are also today, it tends to flip. So embodied carbon becomes the more important one. And this is simply to do with the fact that there has been more attention on operational carbon. Legislation has been more advanced. The grid is being decarbonized, and so on. So the focus really now is coming on the embodied carbon. And I think the topic of embodied carbon, we also need to think about, it's really most significant in places in the world where we will build a lot. So as you can see on this graph, we have continents, countries where it's more that we have a lot of existing building stocks, but then in other parts, we will build a lot of new buildings. Africa is where we will build a lot of new buildings, China and India as well. So the global building stock, if you look at this on the whole world level, is about to double in size by 2060. So everything that is so far built on this planet will be built again in terms of quantities. And this, I like to always use examples. So this is about one city of Paris every week. So we will build a lot in the years to come. And if we don't think about this whole question of embodied carbon, then it will have a significant impact. And then there's another concept to really understand is carbon is not simply carbon. It has a different impact or a different value. This is showing when you go through the life of a building, when the carbon is emitted. So the green stuff is the carbon that is emitted, the embodied carbon that is emitted when the building is built. And then the blue peaks that you can see is every time the building is being refurbished, there's of course another chunk of embodied carbon that is emitted. And the operational carbon is more something that is emitted throughout the whole life of the project. But every CO2 that is emitted today can already heat up the atmosphere as of today. So they don't really have the same impact. And this is really showing that focusing on the embodied carbon today is so very important. Now, when we understood the concept of embodied carbon, let's now look at a building and see where does this embodied carbon sit within a building. And it's showing that over half, about 60% sits within the superstructure and the structure, which is kind of logical because it's the carbon linked to the stuff, and a lot of stuff sits within the structure. Now, if we put all of this together, keeping in mind 40% of all CO2 emissions globally come from the buildings. We look at the buildings, it's about 50-50 between embodied and operational. And then zooming in of that, 60% of this is the structure. We come to the conclusion that all of the CO2 that is emitted globally, 10% of this is really connected back to the structure. And it's something that we as structural engineers can have an impact on. And I would argue also that we have a certain responsibility for reducing. So it's just to make this point, we are a really big part of this problem, or call it a solution, which is more what we should focus on. And also maybe on a slightly different way of representing this is a little case study for our daily work. Put this into context, if you fly once around the Atlantic from London to New York, you emit 1 ton of CO2. Assume you're designing a building as a typical structural engineer of 15,000 square meters. And let's take an average value of 300 or 330 kilograms of CO2 per square meter. This is just for the structure. You design, or you're responsible, involved in the design of 5,000 tons of CO2. Now, if you only make that 20% better, you are saving 1,000 tons of CO2. So it's like skipping 1,000 times flying around, flying over the ocean. So it's not to say that everything we do in our personal lives doesn't matter, but I think it's really to highlight that as professionals, we have even a far greater responsibility. And this is really where we can have a big impact. Okay, I have to run through a few fundamentals just so we have kind of the same vocabulary to talk about further. So this is basically the methodology that we use to report on carbon. So it starts with the carbon, everything that is linked to building the building. So you have extracting, transport, manufacturing, transport again to site, and building the actual building. So this is what we would report under A scope. And then we have everything, all the carbon that goes, which is linked to the use of the building. So this is anything that will come in when we have repairs or maintenance and so on. And then of course here as well, the operational carbon, the one that we have that is through the use of the building. And then of course, how are we gonna afterwards dispose of things? And then there's something beyond the A to C, which is the question about what happens if we want to reuse and so on. So A modules is what we call upfront carbon. Then we have the operational carbon. All of this constitutes the whole life carbon. And then of course the question, future benefits or burdens, if we can reuse some of that on a future project. And this is just a link to the circular economy. Where I'm based now in Luxembourg, this is also a very hot topic, but I think one thing to understand is also that there is a difference in the timing of this carbon. So when we move through a project, this is showing the carbon through the different stages for a typical building. So we have a lot of the upfront carbon during the construction. And now if we design this building for deconstruction, well, we will increase this module D, which is basically the potential for reuse. And so negative means good, so it will reduce the kind of balance of carbon. But really, this is also a timeline, so this benefit comes in really late. But if we can reduce the amount of material we use initially in the project, this again will have a much bigger impact. Going back to this time value of carbon that we talked about today, this will really make a big difference. How do we calculate embodied carbon? It's basically, it's a very simple equation. You take the quantity of your materials in your building and you multiply it by a carbon factor. It's probably one of the simplest calculations that we as engineers do, but of course there's details to consider for the quantity, where the kind of boundaries of your system and what you consider and what not. And carbon factors, of course, depend on where this material comes from geographically, whether it's a kind of average value or manufacturer value and so on. But this is really the basic of it. And there's a lot of guidance out there now on how we calculate embodied carbon. One of them, I would say the best one that's been produced by the IABSE is this guide here, which really clarifies what you have to consider with all of these factors and the boundaries and so on. It's free. It also has a shorter version. So I can really encourage everyone to have a look at it and get up to speed. It's really not that hard. And then there's also tools that come with it again by the IABSE, which is like a spreadsheet version where you can import your quantities and pull the carbon factors from a database or import your own, and which make it really very easy. A few more words on other guidance and tools. I'm not going to go through this. I tend to use a lot the IABSE resource map, which is basically a map which has everything, not everything, but say the most relevant publications on it by the IABSE on all of these topics. Some of it, of course, will be in this presentation, but for further reading, I can really encourage people to go there. Design for Zero, a whole guide on this as well. RBA structure plan of work I like to use when we think about what do we have to do at different stages of the project as a structural engineer, and what are the specific tasks to this topic that we really have to add. The LETI Climate Emergency Design Guide, I think, is really good for when you don't want to just think about embodied carbon, but really about cutting carbon in the whole of the project, also in collaboration with the architects, and then also how we can get all of this information into a client brief. And then there's tools out there. I quite like to refer to One Click LCA, who've done a really good job at advancing this topic as well. There's a lot of guidance published from them as well. And they have a tool, which the basic version actually is free to use. And it's so what they do is they collate all the EPDs of the different materials from different countries. So it takes away a lot of the work that we'd have to do typically ourselves to get a hold of these EPDs, which also have to be verified and kept up to date. So they bring them together and have a tool also where you can straight away calculate the embodied carbon of a project. And when it more comes to conceptual design and this question of parametrics and how does carbon and cost, how can it be optimized in a project? The Panda tool by Price and Myers is also really exciting. So you have to contact them directly if you want to get more into this. But moving on, so the fundamentals, of course, so we then have to look at what is happening at a regulatory basis for all this topic of carbon, especially embodied carbon. And I want to start with one thing, which is before we go into kind of laws, but there has been movement. So this has started in the UK with Architects Declare in 2019. So architects basically getting together and saying, we really have to do something about this. They signed up to this. It's then moved on to engineers declare, or contractors declare, and everyone, and it's now grouped under built environment declares. And you can sign up to it. There's now 28 countries represented and over 7,000 practices. And it's not necessarily about giving details about how you're going to do it, but it's basically saying we have to do something about this. We have to drive the carbon down, and we recognize our responsibility on this topic. But of course, that also has to be connected with some real actions and targets. So every country, of course, based on the global agreements, the Paris Agreement, and so on, they have to put this into local legislation, which slightly maybe depends on the country you're in. But there's also global roadmaps, which tend to be produced by someone like the World Building Council or others that you can see on the right. And the targets for the whole of the built environment is that we have to reduce or cut by half our emissions by 2030, again with the aim of getting to net zero by 2050. And now if we look at just the building, it basically means that you have to get to net zero in operation by 2030, and at the same time by 2030 have a 40% reduction in embodied carbon, and again by 2050 it's just net zero throughout. So those are our targets. Of course, we'll look into how are we actually going to do this, but I think it's important to keep this in mind. This is what is needed so that we stay on track with this 1.5 degree warming that we mentioned earlier. Now, looking at the actual legislation, so what do we have to do? I think the first point to make, of course, is that not all the countries are in the same place. Operational carbon has been regulated for much longer time, of course. So what we see is that the embodied carbon tends to get regulated first in countries which also have had those regulations in place for a long time and which have a very low carbon energy grid. So in order to cut more, they also really are now forced to look at the embodied carbon. But it's not just those countries, it's really moving. So the countries that have already a limit on the embodied carbon in a new project are countries such as France, the Netherlands, and Denmark. I showed here the example of France. This is kind of the closest to me, which starting from this year, you actually have a value of embodied carbon per square meter, which is something just below 750 kilograms per square meter, that you have to stick to, I think, even in order to get building permits. So it's coming. There's other countries such as the UK and Germany who have the requirement to calculate whole life carbon on the project unreported. There aren't necessarily limits yet, but it's really moving. And if you want to find out where each country in Europe is at, I can refer to the guide here on the right, which has been updated recently and is the best reference I could find for this. But I think that the point here to make these frameworks, be it roadmaps or even legislation, it develops differently depending on where you are in the world, but it is changing. So this kind of mention or inclusion of embodied carbon and not just operational carbon has been doubled globally in what I call frameworks, so be it in assessment methods, sustainability assessments methods, or be it legislation. So it's really speeding up. And so it's just a question of time when these embodied carbon laws will come into place everywhere. And even the EU is now starting to, or is working on putting all of this in legislation as well in the coming years. Now, moving on from legislation to benchmarks. So of course, if we have a target of getting whatever 40% better by 2030 on the embodied carbon, we need to know where we stand today. And there have been studies done in many countries, and of course the values differ slightly. What I want to share with you here is a study done in the UK, published by the IABSE, which shows the embodied carbon on different types of projects. This is cradle to grave, so it's really from the first stage to the last, of course, not looking at the circular economy, but still the whole life. And it's not just for the structure, it's all the building elements. And we can see that there's quite a range, but we're kind of maybe at, say, 1,000 kilograms per kilogram CO2 per square meter on average for the embodied carbon. Now, I just want to use this value to make a point connected with what I said before. So let's take these 1,000 kilograms of CO2 per square meter, and we looked at how much more we will build from now until 2050. So this is the billions, 144 billion square meters will still have to be built to respond to the population increase that we are expecting. So this will be leading to 144 gigatons of CO2 by the year 2050. And now let's compare this to our carbon clock that we looked at before. So in order to stick to the 1.5 degrees warming, we have our budget is 280 gigatons of CO2. So really to show here is that this is half. So just this question of embodied carbon in buildings could eat up half of that budget. So this is not even talking about the operational buildings, and it's not talking about any other sectors out there. So it's hugely important that we get our heads around this in order that it will not be, say, our chunk or the chunk that we're responsible for that will eat up quite a significant part of this. Moving from benchmarks then to targets, once we know what the average is today, we can then look at, okay, how much better do we have to get to stick within the limits? And the system that is being adopted here is a very similar system to that we've seen for the operational carbon. So we have a kind of color-coded system with categories that stand for a certain amount of kilograms CO2 per square meter. And whilst we're today, say, in category E, we have to shift this peak back. Maybe we should aim for C today, but it's really A that we should be aiming for by 2030. And these are targets produced by, well, this is RBA in the UK and LETI. Now I'm showing here what LETI is saying. So it's saying for different building types, currently we are in the category E. And these are really the targets that we have to aim for when it comes to embodied carbon. This is the upfront carbon. So we also have to be paying attention a little bit for what stages this is given for, but it's really the big chunk of the embodied carbon. So this is where it has to go. And what is quite interesting to see is also that there are people, also developers who are taking this really quite serious, and they have, like Governor is one of them, who have actually made statements of what kilograms of CO2 per square meter they will be aiming for this time by 2025. So people are implementing this, and I think we should all be really focusing on that. What I showed before was more for the building as a whole, but of course we also want to know what does that mean for the structure. And the IABSE has published a similar system. It's called the SCORE system. A little bit different. These categories all stand for a band. So 200 to 250 kilograms square meter of CO2 per square meter means you're in C. And this is not really making a differentiation between any type of building as we saw before for the RIBA, but it's basically saying, okay, today we are the category E. We have a certain carbon budget left, which is what you see again, the area below the curve. And if we want to stick within the limits and get to 0 by 2050, every year we have to become a little bit better. So by 2030, we should be aiming for 150 kilograms of CO2 per square meter or less. Okay, so now that we know about embodied carbon, about the different targets, the question is really, okay, how on each of our projects, how do we have to go about this to achieve it? And I think one of the important things to really understand is that as we move through the design stages of a project, things become more and more set. So the opportunity to really change things goes down. But at the same time, the cost of really changing something goes up. As we know, to a certain point, probably sometime later on, when you want to change something, it will cost you more than the value you can actually get out of it. But this is really to make the point that if we want to improve things, it has to happen at the very early stages of a project where this value gain, this impact that we can have at the lowest possible cost is the greatest. And using the same logic again, it shows the carbon reduction potential as you go through the different stages. So at the very beginning, it's highest. This is a strategy. It's kind of leaning and very much in line with what the IABSE has produced. I'm just like structuring it in the way that I understand it best, but it goes to this topic of first building nothing. This is really about the brief. Building less, this is a lot about the collaboration, the design team working together with the architects to really reduce things. Build clever, this is where a lot of our ingenuity will come in, and then build efficiently a lot in collaboration also with the construction industry out there. So I want to spend some time to go into a little bit every topic here and explain the challenges that are linked to it. So the first topic, build nothing. Well, you might say, this is really quite controversial. I'm an engineer. My job is to build buildings, or at least to design them, and then to get someone else to build them. But I think this is actually not what we are there for. I think we're there to solve problems. I think if you even want to go further, I think we're there to understand problems, to define them better, and then find solutions for them. So building can be the solution, but it doesn't necessarily have to be the solution. And I think it's really there where we can have the biggest value as well for our clients, and in some way also future-proof ourselves. Because as we know a lot with technology and automation, say the traditional job that we've been making of simply calculating things will disappear. So this is really, I think, where we have to position ourselves, and also where we can make the greatest impact. Of course, this whole point of build nothing will be more relevant in parts of the world where you have already a big existing building stock, so typically North America and Europe. And the greatest opportunity is also for projects where you can find low occupancies, for example, hospitals, schools, airports. So question like, how can we optimize the space utilization? Can we solve the problem in a different way by reorganizing things? Can we change schedules of flights so that we don't need additional car parks, and so on? So there's a lot of case studies out there on how engineers, design teams have been able to challenge the brief, solve the problem in a different way. And I can refer again to the publication of the IABSE that has these case studies. And of course, it leads to the next point, which is, well, if we don't want to build, then of course we can't demolish really. And I think that's still something that we see happening in a lot of parts in the world, is that, well, also where I'm from, or where I'm now. And it's this idea that, well, it's better to knock down this building to build a new one that is maybe more energy efficient and so on, without really going behind this and proving in a in a say neutral way, unbiased way, that this is really true. And thankfully, I think, at least in the UK, the public is waking up to these realities and actually also asking for this, so that we stop just knocking down everything. If you now come to the conclusion that simply building nothing is not going to solve the problem, but we have to build something, then I think the next question to ask is, can we reuse parts? So can we, for example, reuse at least the foundations, the cores, the facade of this building? And maybe if it's not of this building, then okay, can we not reuse parts of another building? And also there have been guidance produced more and more on how to do it. Steel, of course, is a kind of logical candidate for all of this, and this is also in line with the point I made before about the circular economy. This is really where we can where it comes in and where we can have a big impact today. The next point is then to build less. Of course, we have to reduce, and this is really a question about the demand. What do we design for? Do we really have to build do we need that many square meters for whatever function we're trying to create? Can we reduce that? Can we be more clever about the planning of that space? A lot of buildings have quite low occupancy. Can we combine functions so that we don't need to build that many square meters? So this is all about that. Basements, I'm not going to go into that in this talk, but basements are really quite hotspots when it comes to embodied carbon. So can we not have a basement, for example, and do it in a different way? And also the question of height comes in, of course, again, a topic which we could look into in a lot of detail. This is a study produced by Bureau Happel, which shows as the number of stories go up, the embodied carbon also goes up, which is logical when you think about the impact on the structure that it has. So above 6 stories, we can see really that upward trend. And then, of course, this whole question of repurposing and refurbishing. So also this is kind of connected to how can we keep things for longer? And this is thankfully something that we've been doing already, but we have to do much more. And I think it's also where really the creativity comes out, when you have to work within existing constraints and see how can you make it fit. I think that's a really big part as well. And then next, how can we simply extend the life of a building, not necessarily by refurbishing it, but making sure that, you know, we can keep it in use longer for different uses as is. And of course, the adaptability, so working with the architects that we can change things around is important, but also this question of flexibility. And so this is a topic that structural engineers is important to structural engineers as well, because this leads to this question for how much loads do we have to design today if we want to make sure that maybe the client decides they want to use it for higher loads or a different way in the future. What does that mean? And I want to show on the right, I reference a study that I found quite interesting, which looked at typical building, flat slab that they designed for a higher load to deal with this this flexibility. So for kPa live loading +1 for partitions. And they looked at how much carbon they get. And then they looked at another scenario where they maybe design it for more typical live loading. And then what would it mean if they had to strengthen it later, the additional carbon that goes in? And they can clearly show that designing for less today and maybe accepting that you have to strengthen later is less carbon, so about 10%, which looks not so much, but when you multiply that by the kind of quantities or the square meterage, it can become quite significant. And here you also have to keep in mind that, again, the carbon that we emit today has a bigger impact than the carbon later. So it's not quite comparable. And then the last point in this build less chapter is then, of course, how can we design for future reuse? Of course, the benefit for that would not be felt today, but it's something that we'll get later. But still, this is something we should consider today, of course, without forgetting all the other parameters that we'll go through. It's an example I'm showing from Luxembourg of a recently pilot project that we've done, which I think has shown that it's possible and should be done more. Okay, the next category then, moving from build less, is this category of build clever. And there's again a few strategies within. I think the first thing to be aware of is that a lot of the embodied carbon sits within the floor slab. So this is a study by Tomasetti, which they looked at the different building elements from beams, floors, walls, columns, and foundations. And they clearly showed that a lot of it sits within the floors and the foundation. So if we have to get started somewhere, this is where we should focus. And then, okay, if we want to reduce the CO2, one simple way of doing it is to reduce the spans. And of course, this will only be possible to a certain degree, but we can really show that if we manage to slide down on this line, we can reduce the carbon in a simply easy way. Transfer structure is another one. This is an image of a project I worked on in the early years at Arup, a building in Doha, where we wanted to create this kind of split or this kind of gap in the building. So the way, as you can imagine, it worked, the loads had to go up with a big transfer structure at the roof, and then they were brought down by the cores. And although we didn't do these calculations at the time, I think it's easy to see that that was clearly not the most efficient solution from a carbon point of view, as we had to bring up the loads up and first and then down. But it doesn't always have to be about architectural statements. I see a lot of cases where it's simply a lack of collaboration at the early stages of a project, where grids are not coordinated between engineers and architects, and we just end up with transfer structure everywhere. Of course, we can make it work, but the cost, carbon cost, but of course also project cost which it comes is significant. The next point within this is the use of more efficient structural forms. So the basic concept is tension and compression is more efficient than structures in bending. And so slabs is really where we have to focus on. And when you look at a flat slab, we have a lot of this material in the middle that is not really in the middle of the zone, which is really not needed for that bending. So it's where we really end up with something that is not efficient. And this is a study done by Burr Happel, which has looked at the embodied carbon, keeping the same material, but just changing the system. So I'm going from flat slab to beam and slab, post-tension slab to waffle slab. And as you can imagine, the numbers of carbon per square meter really is brought down. There's different ways. This is just one example, but to think about how can, with the use of a different structural form, how can we bring down the carbon is important. And then going into materials, and this is not yet about specification, but this is really more about the choice of material. And it's something that is important, again, at the very early stages of the project, where we do conceptual studies, and to look at, by changing the material, by using it in the most appropriate way, how can we make savings on carbon again? And what we can find is typically by moving from a concrete option to steel and then a timber option, we do reduce the carbon, but of course this has to happen in kind of a logic with the project. If the spans are not appropriate or other factors come into play, this might not be the conclusion, but generally this is where timber should definitely be studied along with other materials. And then the loading, I mean, we all know this is a study, but I think this is logical to structural engineers. As we increase the loading, the CO2 per square meter will also go up. But it's more to really make the point, can we challenge the loadings that we're designing for? Typical office, we probably design for something more close to 3 kPa, but a normal occupancy, or say even a slightly more extreme version of the normal occupancy, would get us more close to 1. So can we question this? Or at least, I know it's not always easy to do that while staying within the code, but life load reductions should be something that we absolutely do on every project. And also using time for refinement as we go through the project to really review the loads and see if we haven't done maybe conservative assumption at the beginning, and we can really bring that down. And also, this I found quite interesting, trying to really bring this at an even level between the disciplines. if you look at for how many people we design when it comes to ventilation or fire and so on, and then you compare this for how many people we design for in terms of structure, there's a real big gap. And so being able to look into this and question it and make sure this is reasonable is another important point. And also SLS design criteria. Again, do we when we look at the facades, what kind of deflection limit do we really need? Can we work with the contractor to really see, is this what is required? The same for internal partitions. Can we pre-crumble slabs? Is there a different way through stiffness, not just by adding material, that we can solve this? That's another point. Okay, then the last category, this is, I'm also showing always here on the right, the kind of impact. Of course, these are not absolute numbers, but it's just trying to show you where we have the biggest impact and as it goes down. I think when we talk about driving down carbon, often the idea is, well, we have to optimize, and optimization is clearly important, but it's again, just to show it's not what all of this is about. The strategy is much wider than that. But when we look at optimization, this is a study that was done again in the UK with the reference here below, about to what degree, what utilization factors typical beams in a steel building are used, and this is going through quite a large database of steel buildings. And what was found is that it's often not going much below 80%, and the average is probably somewhere around 50%. So we're really not trying to squeeze out or to push this to the limit. Why are we not doing this? There's also been some studies done within the industry. There's a report by Macon which looked at this, but I think it's often done because we want to make it easier to build, because we also know that there will be errors maybe, or that there will be changes coming up lately. So that's why we don't push it quite so hard. But also, if we're honest, I think it's also because we haven't really been forced to do it. And of course, it takes more effort, it takes more time, and there's nothing been in it. And I think depends on the country we're in, but where I'm now, it's also that our fees are often linked to a construction budget and then also construction volume. So if we don't align these two goals to really have a commercial benefit whilst also driving down quantities in carbon, then I think it will be very difficult to solve this problem. So what do we have to do? We should be pushing, if this is like the typical utilization that I would be designing for the very early stages, this range should be pushed more towards the 100% during the later design stages. And it should really not just be that we have a maximum utilization, but we should also be designing for minimum utilization. And I think this all comes with the logic that the IABSE has also been very clear about, that it's not just about safety. If we want to solve this, we have to put carbon really at the same level with safety. And it's not to say we have to compromise on safety, it's just to say it has to be looked at in the same priority. And then again, in the chapter of build efficiently, we can do also things about looking at our specifications. I'm not going to go into the detail of this. This could be something that could be done in a follow-up webinar where we really look at each single building material or the main ones and look at through the specifications what can be done. But with concrete, we of course know by specifying cement replacement, we can also drive down the amount of CO2. And then there's a whole other list of things we can do in this build efficiently chapter, which is more to do with offsite construction, using waste, building locally so that we minimize transportation distances and modern methods of construction. Again, things for another talk. So just to summarize this, I think there's one mantra that has to be kept in mind if we want to have a chance to win this battle, and this is this mantra of use less stuff. It's somehow as simple as that. Of course, within it there sits all of these things that I went through very quickly now, again with different hierarchies. But I think this is really where we have to understand that's where we will make the difference. And of course, there will be about specifications. And in the end, there will also be the need for probably some offset. But this is where we really have to come in. And this is, again, made very clear by the I-E. So quickly, when we work on projects, what should really be the approach or the actions that we take at the different stages? So I think the first, of course, this is what we're doing here today, and which I hope we can be doing together much more intensely in the coming months. It's about education, of course, getting ourselves up to speed about this whole topic, reading up on it so that we feel comfortable really to get going on this on our projects. The next one is to own it. I think we're all still a little bit, or we have been at least in this mindset of, well, but we cannot do so much. In the end, it's the client's decision if they don't ask for it, or then it's the architects kind of blocking it. Maybe they're not so interested in it. But I mean, we've looked at this here. The structure is such an important part. And I think it's about us making that case, showing this to our clients, showing this to the rest of the design team and saying, you know, we just don't have the choice. We own this and we will do something about it. Then, of course, calculating embodied carbon, it's really not about getting the number exactly right. It's not possible anyways. Carbon factors, they change. Information we take is probably a few years outdated. It's really not about that. It's just about getting started, getting a big idea of how do things compare, what is the magnitude, and then using this really as the driver. So using it to compare the options, as we were saying, conceptual design, looking at how one option compares to the other. This is really how we can make a difference. Of course, it's about collaboration. It will be about doing this together with the architects, the MEP engineers, and also the client to really see how can we measure up these different solutions and then drive it down. I think what we see in some parts of the industry, some companies already saying, okay, this year, the average of all the projects we designed had X amount of kilogram per CO2 per square meter. Next year, we want to be 10% better, which is totally feasible with that strategy that we lined out. So we will drive this down and we will commit to do it. And then, of course, sharing this, sharing the lessons learned, sharing where the challenges were, or also just how you did it. More of this is needed. And then advocate so that all of the people within the industry are really joining on this. And again, I think IABSE is a perfect platform to do this. So this is really only making a start, but I hope you can all help with this. And then I want to just say one word on carbon and cost. This is, of course, something that comes up in a lot of the discussions I also have with people. Of course, everyone wants to know how much it's going to cost this. And this is a graph I took from Climate Emergency Conference by Expedition Engineering. They presented this, and I thought it was really quite neat. So when you look at it, increase in cost, decrease in cost, to eventually get to project net zero by doing all these things you can see on the right, I think it will be difficult to argue that our projects will become cheaper. It will come with increasing cost. But where we are now, and this is this kind of first part of the curve to really drive these carbon emissions down, this is what we have been doing. And this is like the low-hanging fruit. These are all things that we can work on today. There's no obstacle to do it. And I think, you know, we can show that because in the end it's about using less stuff, we will be able to also decrease project costs. But the information, of course, on this, the case study, more of it is needed to hone this in with clients and show them, okay, this is an example of projects where this has been done, this strategy, and this is actually the cost reduction we got. And this is a topic that I really want to focus on more of my attention on in the future, because I feel this is what the discussion with clients often comes down to. Okay, closing this up, but just a few messages for, I think people on this call might be from different backgrounds. There are certainly also people from academia here, where it's a topic that I think is interesting to all of us. So if we want to achieve this, of course, it has to start with education, the way engineers are trained at university. And I would like to argue that me, definitely. I think the generation before me too, we were maybe more trained, like here on the right side. So we went really deep in a few topics, but maybe we didn't get enough of knowledge in the wider topics around, and didn't maybe understand how they all fit together. And I think this is really already linked to the question of then how do we get the right people to become engineers in the first place? And I'm quoting Tim Eibel here, which is something he said at a conference I attended a while ago, which I think really honed this in. And he said, if you're good at math, but you actually prefer to do other things, then you should become an engineer, because it's so much harder for someone who's only interested in math and physics to make them aware of maybe environment, or I don't know, architecture, art, economics, and so on, than if you have someone who's reasonably good at math already and who's also really passionate about the other things. So let's look at who we really attract into the industry so that we can make that change within the next years to come. A message to employers, I think one thing here to understand is that maybe the workforce was coming from this category of people, baby boomers, Generation X, but now we're really seeing that the majority of the people working in the built environment maybe are coming from this generation, and there's a fundamental difference, I would say, that you probably know, but there's also studies on that, which is that baby boomers, Generation X, maybe they were more interested in safety or salary or things like that, but this generation is actually working quite differently. What they are interested in is mostly purpose. So they want to feel that what they do in their life, including their professional life, is having an impact and is meaningful. And this is also shown in certain surveys that have been done, that they really do their choices based on their values. So if you're an employer within this webinar and you want to keep on attracting the best talent in the industry, think about how you can give these people value. And I think the topic we just discussed is just a perfect opportunity for that, and a much needed one as well. And then a final message to engineers. There's never been a time where our skills as engineers have been most needed than they are nowadays, and it's urgent, and it can have a really big impact, as we were showing. So I would argue it's the golden age of engineering. It's exciting to be an engineer, and then this time I think we just have to learn and make sure that we use our skills in the right way. So I'm going to leave you with this. I'd be, of course, happy to talk more to any one of you on this chat, to go more into detail. You have my contact details here. You can also find me on LinkedIn. And yeah, and I hope you have lots of questions that Ian and I, we can look at together.
Lee, thank you so much. Thank you very much indeed. If we were all together in person, we'd have a round of applause. That was really first class. Thank you so much. Wonderful introduction to what is a very wide and very diverse topic, which affects us in so many different ways. So thank you so much for sort of capturing all of that and somehow packaging it in a way that we can get hold of. And as I say, this hopefully is the beginning of what will be a series of things in which we would be able to look more closely at some of the individual specifics that you've touched on. Please do, everybody, if you have questions, put it in the Q&A. There are some there already, and some we can probably dismiss really quite quickly. So, for example, yes, some are asking whether these slides will be available. The whole webinar has been recorded, and so you'll be able to find that on the IABSE website shortly after this this webinar. So just a couple of questions on timeline. So in the valuation of your carbon for a building, what is the operational life that's been assumed in calculating the whole life carbon? A couple of questions on that issue.
Yeah, and they, of course, you have to always look at the same duration. I believe it's 60 years that you would normally consider it at. I think when you go to the ISTRAC-D design guide that looks at how to calculate embodied carbon, this is also mentioned there. But yeah, of course, it's important that we always look at the same time, because otherwise the results that we get will not be comparable. But I believe it's 60 years.
Okay, that's very useful to know that. And it's important that, as you say, we are consistent with that. Simon asks a question, Simon Wadsworth, a colleague of mine, on the question of steel. We know already that steel has got a lot of recycled content, but the question then is, again, rather than on the timeline, when should that carbon saving be used? Is it at the beginning when the material is purchased, or if so, maybe at the end of the building's life when it's recycled? How do we avoid double counting? Do you know how that's dealt with?
So say that again. When should we count?
When should you account for the saving, the fact that the steel has been recycled? Okay, so it's been recycled already. So at the beginning of a project, you're using steel, which is already in the UK, it's something like 85% of that steel has already been used. So when do we measure that and allow for it? Is it the beginning, right at the beginning of the thing, or at the end when the building is recycled? Because otherwise you're dangerously counting twice.
The fact that you are using steel from a recycled source, or which has a certain amount of recycled steel in it, is reflected in the A module. So it's the modules that are linked to the material that you're using in your project today. So this is why it is important at some point as well to go into the detail of where's your steel coming from, geographically, but possibly also the manufacturer, and to really get into the detail of that. But the other topic of the reuse, the future reuse, that would be something that you report separately in the module D. I hope,
And on that module D, there's a question from Gustavo. He asks, how would you manage the allocations when working in module D? There isn't much information about it in codes and standards. How do we?
I don't think I can answer that one. I think there's more information out there. There's someone called Penny Gowler who talked about this in some of the I/E conferences as well. But I think, I think that's something we'd have to look into more detail. How the module D is reported.
I mean, I think inevitably there's a lot more to come. I mean, I'm just going to take Chairman's prerogative and throw a question at you. I'll come back to some of the other ones as well. I mean, you make a very, very clear point about why we need to simplify what we do, have simple structures which are efficient. And you use the example of a building that you were involved with Arup, of a building in the Middle East with a sort of slice taken out of it in the middle, and how that was an inefficient approach. Is this going to change our kind of expectations and architectural ambitions? Because you see so many buildings, don't you, where the architect has got an ambition for doing something a little bit elaborate, which is not efficient. Are we going to end up with a range of buildings which are much simpler in future? Does that affect the building styles that we build in future?
Yeah, it's an interesting question. I do think it will affect the things we do. I think we've moved from the fact that we can do something. We've been able to be much better at representing complex geometry and also manufacturing it. It's led to that, because it's possible, we can do it now, and that's why we do it. But I think we will have to move away from this. We know it's possible. We know we have the tools to do it, but we don't want to do it anymore. And this is clearly not something that's just going to be us as engineers. Yes, we can also calculate these things. We can design them, but it's not where we see our main challenge and our main satisfaction lying anymore. And I see it completely as a joint effort between engineers and architects to say, okay, we have a different kind of aspiration in our designs. And I don't think at all that the result of this has to be dull. I think it can be extremely creative to work within these parameters, because you're so much more constrained, and you really have to understand, how can you make all these things fit together, still conform to the brief and so on. So I think this is where creativity will really come out.
And inevitably the client has to be part of that story, doesn't he or she? Because the aspiration of the clients can sometimes be the thing that will define what sort of architectural style that we use. But certainly walking around the city of London, there's so many inefficient buildings that you cringe at when you think of it in these terms. So it'll be interesting to see how things develop. There's a couple of very good points here about, you point out utilization ratios being too low and how we're not being efficient with the use of material. But of course, both Simon and Phil Quach has said, in effect, it's quite useful to have that extra margin, because when it comes to future reuse and so on, repurposing makes it easier. So there's a little bit of a kind of challenge, isn't it? Yes, we want to have maximum utilization as far as possible, but lower utilizations actually make it easier to repurpose a building in the future.
Yeah, I mean that I was more focusing on a steel building when I was showing that slide, but I think it's relevant for all materials. Of course, if we build in that extra capacity today, it will make it more simple in the future, that for more scenarios we can simply say, well, it's still fine the way it is. But I think for some things that are really difficult to change, for example, floor to ceiling heights, this should be coming into play, because you cannot really do something about it. But if this decision is for something where you can actually do something, the kind of capacity of a beam or maybe even a floor slab, which you can add additional reinforcement, then I think we should really question this.
Yeah.
And again, it all comes down to this carbon budget. Think of this bag of carbon you have available today. Every time you take a design decision today for a future scenario, you're pulling out of it. And what is the point if in 10 years time that bag is empty and we end up with all these buildings that, yes, that will be really great to have future flexibility in the future. It's, we've already kind of dropped the ball by that point. So
Right.
I would be very careful with going down that strategy.
Yeah, I agree. We're going to need to draw to a close fairly shortly, I'm afraid, but there's time for just a couple more. I mean, in fact, some of the questions here are things which I think we want to pick up in future presentations of this sort. So, for example, there's a question about load factors and material factors. You touched on the need to address things like loading and so on, and maybe there is a scope to look at that, and maybe we ought to tackle some of that in a future, more specific and focused webinar in the future. And there's another question here about bridges. You've talked, of course, about buildings, and we've not really touched on bridges today. The answer to your question, Michael, is yes, indeed. There is quite a lot happening in the bridge field. There are people, in fact, on this call, I've noticed, who are very much in the vanguard of that. So again, in future, watch this space, because British Group will certainly run another webinar, or several probably, on the bridge side. But the very similar things are being addressed in the bridge field. But I'm going to leave you with one final question, if you forgive me for leaving out one or two of the questions which we haven't got time for. But here's a question which I can't resist throwing at you. If you had a superpower, and this is from an anonymous attendee, within the means of being a structural engineer, which step, if you were going to choose one particular step, which step would you personally take now to reduce the carbon most efficiently?
Oh, wow.
What's the golden bullet?
That's a really great question. I mean, to be honest with you, I think one thing we will not get around is really to think about the demand side, and I think I've been recently reading this book, Donut Economics, and I think it's a really fascinating read. And as structural engineers, we think our job is there so that we create solutions so that people will become more comfortable, more safe, more everything. But actually, what we've done is I think we've gone beyond that. And of course, I'm going to focus now a little bit on the parts of the world where I'm from. But we're all on the same track, and in the whole world, it's going in the same direction. But we're actually gone to a point where we went beyond that basic need. And I'm not saying, of course, there's the need for delight and the need for pleasure and all of that. But I think we have to really think about how much are we really asking for? Because none of this can be answered through a little bit of optimization here or there, or changing one material to the other. These are all good things, but it's about these kind of basic questions, the kind of, does the built environment we want to live in, and could it not be much more simple, much more, much more pleasant maybe, but not, always more in all kinds of directions.
Yeah. I think you're absolutely right. Managing our expectations. It's very easy, as you say, for us to say that in the kind of, should we say, developed world. And as we saw last week coming out of COP27, at least there's a desire and I think a commitment from the developed countries to help out those countries who have not yet got there, because they've still got the same aspirations. They want to do what we've been able to do, but no doubt it'll be different for them. Tina, I say Tina, I'm actually just reading from Tina, our president, who has just written a comment. Thank you, Tina, for that. It's nice to have you with us. But Lee, bless you. Thank you so much for a really stimulating start to this series, really sort of kicking us off wonderfully. And as I say, I hope you will all be looking out for future episodes. British Group will certainly be taking this thing forward. So please keep an eye out. If you have any questions specifically, you can contact Lee. You've got her details, or indeed me. You can find me very, very easily on the IABSE website. And indeed, if you have suggestions for topics specifically within the context of the climate emergency that we have to address as structural engineers, any specific things that you'd like us to try to organise a webinar on, please do let me know, and we will try to pick that up. So, Effie, I'm not sure, is there anything else we need to do other than to once again thank Lee for a really first-class presentation?
Thank you as well, everyone, for attending. It was a pleasure to be here and looking forward for the next ones to come.
Okay, thank you, everybody. Thank you, Lee, and thank you all of you for attending. Thank you so much for attending.
Bye.
Okay.
Bye.
Bye-bye now.